and I'm guessing everyone can hear me as well. So that's great. And Teresa, if you want to record the workshop, feel free.
Yep. Okay. Thank you.
No problem. Okay, perfect. So hi everyone, my name is Netra Rajesh, Netra Unni Rajesh, and I am a PhD student at Stanford University, and I actually just started this year. So I finished my undergraduate degree at the University of Toronto, specializing in engineering science with a major in biomedical engineering. And today I'm really excited to talk to you about how we can use biomedical engineering to design cancer technologies. So I do want this to be a little bit interactive. So if at any point you have a question, feel free to drop it in the chat, or you can even unmute yourself and just say, hey, Netra, I have a question. I'd be happy to answer. And I do have some time for Q&A at the end. So it would be great if you guys could unmute, and I'd love to hear your voices and any questions you have. Okay, so without further ado, I just want to share the agenda that we're going to be covering today. So I wanted to start off by giving you all a little bit of an intro into biomedical engineering and specifically talk a bit about my journey and the path that I took. We'll then delve into engineering design principles and how you can apply this in cancer research. And I'd like to wrap up with some real-world examples from my own research, as well as some additional resources y'all can look into and a Q&A. So let's get started. So biomedical engineering is also sometimes referred to as bioengineering, and it really depends on the school that you're in, whether it's interchangeable. But essentially what bioengineers and biomedical engineers do are they use concepts in science and mathematics so that we can ultimately engineer new technologies that'll help us tackle human diseases and health problems related to the human body. Now, I know that sounds like a lot, and that's because the really cool thing about biomedical engineering is that it's a very interdisciplinary field. So here I've kind of broken down biomedical engineering into the four main areas, or the four main fields that can kind of be absorbed and are incorporated in biomedical engineering. But I do want to put out a small disclaimer here that this isn't an exhaustive list. And in fact, there are several more areas that can be integrated into biomedical engineering. And that's why it really is such an interdisciplinary field. So the really cool thing is that a lot of the work you can do in biomedical engineering encompasses a lot of these areas. And I'm going to be showing you a few examples right now. So the first I want to talk about is at the intersection of electrical and computer engineering and mechanical engineering. Now, this includes things like prosthetics, rehabilitation engineering, orthopedics, you name it. So essentially, these devices require us to mimic forces that the human body experiences, which is why you need to bring in mechanical engineering. But then we need to figure out how we can use electrical and computer engineering components like motors and things like that to help us actuate those forces. So that's how the electrical and computer part comes in. And right now, there is a really cool push to interface these technologies with the brain so that people can actually control these prosthetics like they would control their own limbs. At the intersection of electrical and computer engineering and material science are research into medical devices, wearable technologies, biomems, which are bio-micro-electromechanical devices. And essentially, they're small devices that can be implanted into the body to fulfill various functions and tackle diseases, and nanotech. At the intersection of mechanical and biological and chemical engineering are things like tissue regeneration, bone engineering, again, how we can design these tissues outside of the body, but still bring in that mechanical component so that they can fulfill and they can experience the loads that the body would normally experience. And finally, the area that my work is in and that I'm interested in is material science and biological and chemical engineering. So at the intersection of these two areas. And this includes research into biomaterials, drug design, drug delivery. How can we better deliver these therapeutics into the body so that we can minimize side effects? Nanomed and nanoengineering. And for me specifically, I'm interested in immunoengineering. So how we can use these biocompatible materials to ultimately engineer and enhance the immune system to tackle diseases. And my focus specifically is in cancer. So I know that was a lot of information, but hopefully that gave you some insight into how interdisciplinary biomedical engineering can be and how many different areas you can really pursue in this field. Now, on the other side of the coin are career paths that you can take. And again, I do want to preface by saying this is not an exhaustive list, and there are many other career paths you could pursue. But in general, there are a couple segregated tracks you can choose depending on how you want to be involved in the field. So if you're someone who knows, you want to conduct experiments and you want to be in the lab and get your hands dirty, generally the two career paths that would be good for you in biomedical engineering are as a researcher or a scientist in a company or as a university professor or industry leader. So, if you want to go with the latter, you would need to do a PhD, which is the track that I'm on, though I'm not certain if I want to go into academia, which is being a professor, or if I want to go into industry and work in a company. But yes, so you would do a PhD in that case. If you want to be a scientist or a researcher and work in a company or at a university, you would be at the lab bench, getting your hands dirty, doing all these experiments. And for that, usually you need a master's degree. If your goal is to bring medical devices into the market and actually work in a company, if you want to be a business associate, usually they suggest doing a master's in engineering or an MEng. And if you want to work in the company as an entry level biomedical engineer, you would need to have a bachelor's degree. And finally, the other side of it is if you want to treat patients and you want to practice clinical medicine, in which case you need to bring in an MD into your repertoire. So if you want to be a medical doctor, you would have to do an MD, which is about 4 to 5 years. And if you want to be a scientist who has the clinical expertise, but also is a leader of their own lab and does research, usually this is translational research, which means research that ultimately would help get into the clinic and be a therapy for patients. You need to have an MD, PhD, and have both of these degrees. And generally, those programs are about 7 to 8 years. So I highly encourage you all to take a look at the American Institute for Medical and Biological Engineering. They have a lot of great information on bioengineering career paths and how you can further immerse yourself in the field. And also they have some cool features of scientists who are already established as biomedical engineers. So that might also be really good insight to get. Okay, so now I want to talk a little bit about the path that I took. And I don't think, biomedical engineering isn't like a one path fits all type of thing. It's very much, you exploring the areas that you want to explore, and one thing naturally leads to the next. And hopefully by sharing my path, you'll see, how one thing naturally led to the other. So, my journey in biomedical engineering and research started pretty young when I was 14 years old, actually. I participated in a science fair, and how that entire thing came about was there was an article in the newspaper which said Wi-Fi causes cancer. And I was 14 years old at the time, and Wi-Fi was coming into our school for the first time. So I know, pretty old. But I was baffled, like Wi-Fi was this really great thing, and everyone said it would be super beneficial to have access to all this knowledge. But then here was this article saying it could cause cancer. So I wanted to see whether that association was true, and I actually designed an experiment that would allow me to test the effects of Wi-Fi radiation on cells. And I ended up doing this experiment in my basement, and I borrowed some equipment from my high school science classroom, set up a little microscope. I had yeast cells, and the whole shebang. And I got to run this experiment and present it at our regional science fair. And this was a really cool experience for me because it was my first foray into research, and it was an opportunity for me to see how I could let my curiosity drive me. And from that moment, needless to say, I kind of fell in love with research. So after that, I actually did end up working in a lab when I was in high school as well, at the age of 16. I worked at the Sunnybrook Research Institute, which is a lab here in Toronto. And I was looking at a project that wanted to inhibit an enzyme called telomerase. And this enzyme is believed to be upregulated or overproduced by cancer cells because it allows them to, proliferate faster and reproduce. So that was the project that I was working on. It was very much genetic focused. Oh, sorry. Is is there a problem? I think there was an interruption. Okay.
No, I think someone just accidentally unmuted.
Oh, okay, no worries. Sorry. So to continue, this project was very much focused on kind of genetic work, and I got to learn a lot of lab techniques and get introduced to those lab techniques, which was really a cool experience to have at that age. This experience actually got me really interested in cancer and specifically looking more at the genetic side of cancer. So, after this opportunity, I ended up working at the Ontario Institute for Cancer Research in the summer between my senior year of high school and my junior year of undergrad. No, freshman year of undergrad. Yes. I'm still getting used to the whole US freshman junior thing. We usually just say first or second year in Canada, but it's all good. So, in this experience, I was looking at the genetic underpinnings of colorectal cancer, and I was working in a lab where we were looking at two specific genes that were implicated in colorectal cancer and characterizing how these genes play a role in progression of the disease. And here I got to learn a lot more about cell culture and how to grow cells outside of the body and run experiments on cells. So after this, I joined my undergraduate degree at the University of Toronto. Once again, I joined the engineering science program there and I specialized in biomedical engineering. And we had this really cool internship in the summer after our first year where we got to go abroad and do research. So I worked at the National University of Singapore. And here I was looking at something completely new to me, which was microfluidic devices and tissue engineering. So we were looking at designing these microfluidic devices where we could grow cancer cells that were derived from patients and test those cells with radiotherapy to see if that would be a good way to move forward. Because it turns out some patients are inherently resistant to radiotherapy. So that might not be the best course of treatment for them. And then after this, every summer after my undergraduate year, I ended up doing research. So this was my second summer. I worked at a lab in the University of Toronto. And this is where I brought in that materials science focus. I was looking at designing gold nanoparticles that would allow us to deliver chemotherapy drugs to the nucleus of cells. And then finally, in the summer after my third year, I was working at Caltech on a project to design a bioreactor for us to produce cancer vaccines. And this is where that immunology interest came in for me, where I wanted to look at immunoengineering in the context of cancer. And we also have this really cool program in my undergraduate degree where we get to take a gap year between our junior and senior year, and we get to go work and actually do a full year of co op. So I was working at MIT in the Langer lab doing research full time for a year. And I was looking at designing nanoparticles as drug delivery vehicles for various cancer therapeutics. And this experience is really what solidified my interest in pursuing a PhD, which brings me to where I am today. I'm pursuing a direct entry PhD at Stanford in bioengineering. So if you have any questions about the path that I took, feel free to put it in the chat or ask me during the Q&A. I'll also share some additional resources if you're interested in learning more about the research that I do. So now delving back into biomedical engineering, I wanted to share some of the courses that I took throughout my undergraduate degree, just to give you a flavor of some of the courses that can help you pursue a career in biomedical engineering, as well as give you the foundational knowledge that you need to move forward in the field. So in general, my program was structured such that the first 2 years were general engineering. So we did a lot of things like calculus, physics, coding, fluid mechanics, all of the hardcore engineering subjects we pretty much did in our first 2 years. And then in our third year is when you begin to specialize. So I specialized in biomedical engineering. And because of that, I was able to have a lot of courses in biology, which included things like anatomy, immunology. We had a lot of molecular biology labs where we learned those laboratory techniques in-house and were able to get exposed to the lab environment and how to navigate that. I also took courses in biomechanics and cells and tissues, regenerative medicine, and organic and biochemistry. But the cool thing is, we also had a breadth requirement, which meant I had to bring in some humanities subjects. And I think this is really where I was able to bring in kind of the thought process that allows you to become an engineer in biomedical engineering. So, some of the courses that I took in the humanities were bioethics, which is kind of at the intersection of biology and humanities, medical device approval, intellectual property and patent law. All of these are things, that might be useful if you want to go in industry or want to start your own company. You want to think about how you can come up with these ideas and translate them into products that can be used in the clinic. But the courses that I found really interesting in my undergraduate degree were these courses called Capstone and Praxis, or engineering design. So Capstone is a course that we do in our fourth year where we're actually presented with a problem and we have to design a solution for it and implement that solution. Praxis and engineering design is a similar course that we had in our first 2 years. And here the problem wasn't biology or biomedical focused, it was just a general um, client that we had to work with and help address their problem by designing a technology. So, what I found really cool about this is I think the engineering design process is such a valuable tool to implement in research. And I want to walk you through what the engineering design process is. So, what is engineering design? This is a diagram that I found off of a website, which really clearly delineates what the engineering design process is. It might be a little bit complicated, and in fact, I think you can break down this entire process into 3 phases. The first phase is what I like to call framing. This is where you're identifying the problem, you're exploring the existing landscape to see what other people have done. Are these problems relevant to other people? So the framing stage is where you figure out what is the problem worth solving and what are other people doing to tackle that problem. The next phase is diverging. And this is where you start generating those ideas and brainstorming. You create prototypes where you can test out your ideas. And that brings you to the third phase, which is converging, where you're actually testing out your ideas, you're implementing them, evaluating them, and figuring out how you can make them better. And then you iterate back into the diverging phase, where you come up with more ideas based on the results that you found and the limitations that you found. So, this frame, diverge, converge process is really key to engineering design. And I think it's a really useful process to implement in cancer research. So, how does this apply? Well, the framing stage is really where you're identifying gaps in the field. You read all these scientific papers, and usually those papers will say, this is what we have found, but this is what needs to be done for the field to move forward. So, what are those gaps? What is the research question that you want to address with your experiment or your project? And here there's a component called a literature review, which is what I kind of described earlier, where you're reading all of these scientific papers in your field of interest and you're looking at what other people have done, what are the gaps that they've identified, and what is a question that you should, pursue, and what is a question that's worth answering so you can create an impactful project. The next stage is diverging. So, in the context of cancer research, this is where you're generating hypotheses, you're designing your experiments, you're figuring out what should I use to test my experiments? Should I use cells? Should I use other models? Things like that. And finally, the converging stage is where you actually analyze your preliminary data. You do statistical tests to see whether your results are significant or not. What are variables that play an important role in your experiment, and you draw preliminary conclusions. And based on that, you reiterate and you continue developing these experiments. And this whole process is what I hope to apply as I embark on my PhD. And I hope that using these, bringing in that engineering design perspective will allow me to generate an impactful project that hopefully can help a lot of people down the line. So now I want to show you a few examples from my research experiences so that you can get a sense of what research in biomedical engineering looks like and how this engineering design process can help with that. So this project that I want to talk to you about was the project that I worked on during the summer that I was at Caltech. And we were looking at designing bioreactors to produce what's called an oncolytic vaccine. Now, an oncolytic vaccine is virus-based, and what it does is you use existing cells to produce these, and once it gets into the body, essentially it gets into tumor cells, and it helps kill the tumor cells through a process called apoptosis, so that when they die, they release a lot of their proteins into the environment. Now, this is useful because immune cells can come along and then they find all these foreign cancerous proteins, they educate themselves and they realize this is something we need to kill. So not only does this help kill cancer cells, but it also helps boost your immune system so that the cells can respond and attack cancer cells. Now, I did a literature review for this project, and there was a paper by a gentleman named Russell et al. And the rest of his team, and this was published in 2013. So this is the premise of oncolytic vaccines. But as I mentioned earlier, you need existing cells to produce these vaccines. But because cells need to be grown at really high densities, you need millions of cells to produce enough vaccine to use in a patient. And currently, a lot of the resources being used are these giant bioreactors, which contain tons of liters of cells. But then the problem here is that they were only able to achieve a cell culture density of 5 times 10 to the 6 cells per mil. So about 5 million cells per milliliter of fluid. Now, that might seem like a lot, but the sad thing is that only 0.5% of that entire volume is used for the cells. The rest is to ensure that the cells get enough water and limiting nutrients and oxygen. So there is a lot of wasted space, which is why we wanted to figure out if there was a way for us to design a bioreactor that would help increase the cell culture density, but reduce the amount of space that we need. So in our diverging stage, we came up with this initial design, which was a tube-based bioreactor, and you would put 2 filters at the ends so that you could keep your environment sterile. And we did computational simulations to figure out how much oxygen would be dispersed throughout the system and to make sure that it was enough for cells to survive. We then designed an initial prototype and we tested it with actual cells. So these are cells called Vero cells, which are from monkeys. And these cells are capable of producing that oncolytic vaccine I talked about earlier. So we actually cultured these cells in our first iteration of the bioreactor, and we were able to achieve 12.5 times higher cell density, which was really promising. But even then, this device could be improved because only 23% of our bioreactor was fully loaded. There was still a lot more space and ways for us to improve this loading efficacy. So then we iterated back to the diverging stage and improved our design by adding in this tilted holder so that we could allow gravity to do all of the packing. And in doing this, we were able to increase packing of these cell containing spheres into our bioreactor, and by extension, increase the cell density that we could achieve. So that's an immuno-oncology related example, but I also wanted to show you an example of how different cancer research can look. And this is in the context of the capstone design course I was talking about, and we're looking at designing a medical device. So we were presented with a problem by a head and neck cancer surgeon, which made the framing part really easy for us because the problem was already there. So the problem that we wanted to tackle is a lot of patients who have tongue cancer undergo a process called a partial glossectomy, wherein part of their tongue containing the tumor is removed and then is either replaced with other tissue that isn't as functional as the tongue would be, or it's sutured back together. So what this means is that the patient now has a new tongue that they have to learn to work with. And because of this, patients usually have difficulty speaking and eating and carrying out these daily functions after they've undergone the surgery. So this brings in the need for a rehabilitation process where a speech pathologist will come in and help the patient retrain and learn how to use their new tongue. And to do this, the speech pathologist takes them through a lot of exercises, but the key thing is they need to figure out where the tongue is reaching the roof of the mouth, because a lot of our speech and swallowing processes are based on the tongue touching the palate of our mouth. So to do this and to get a glimpse inside the mouth, they use what's called an electropalatography device, which I have shown here. It's kind of like one of those retainer pieces, but it contains a lot of electrodes so that when the patient wears it and goes through all of these exercises, the speech pathologist can see where the tongue touches the roof of the mouth because of the electrodes and the electrical signal that's transmitted. But the problem is the device that our head and neck cancer surgeon was using contained over 60 electrodes, and each of them had to be placed one by one and wired one by one. And because of this, producing one device took over 20 hours. So we were tasked with figuring out a way for us to reduce the manufacturing time and make these devices more accessible and easier to manufacture. So initially, we thought it would be really cool to bring in a printed circuit board, which in which all of the electrodes would be pre-printed, all of the wirings would be pre-printed, so that basically you just have to, show this design, send it to a company, print it, and then you have it. So we initially developed what's called a solid PCB, which you can see in green over here. It's a solid circuit board for us to make sure we can test the connectivity of all the electrodes. And we were actually also able to work with the speech pathologist and reduce the number of electrodes from 60 to around 30 electrodes, which allowed us to reduce the number of electrodes we would need to put in the device and the number of wires that would need to come out of the mouth. So after initial testing of the design, we were able to confirm functionality. We were down to 31 electrodes, but the device we created wasn't flexible. And as you saw in the palate piece, it has to be able to conform to the shape of the patient's palate. So to do this, we reiterated through our design and we developed a flexible version of this printed circuit board, which you could then fit to the palate of a patient's mouth and shape it so that it would be molded. And we also added in an external signal component and a user interface so that every time the patient uses it, you can see electrodes light up on a screen, which is useful for a speech pathologist. So those are two examples, all in the realm of cancer research, all in the realm of biomedical engineering, but entirely different. The techniques that you use, the skills that you get from these experiments, the skills that you need to perform these experiments and carry out these projects are all very different. And I'm hoping that in these examples and through sharing these examples, I can show you that biomedical engineering is interdisciplinary, but that's where the strength of the field is. You're able to bring in all of these different concepts and work with different people. And ultimately, I think it is that interdisciplinary nature that makes biomedical engineering so innovative. So the cool thing about all of this, is you can generate a really positive impact by pursuing research and projects in this area. You're able to tackle global healthcare challenges, work in an interdisciplinary environment. If you're working in research and doing a PhD, you can generate new knowledge, things that people haven't seen before. You can push boundaries to innovate, and you can develop your work and hopefully bring it into the clinic so that you're able to positively impact the lives of patients. But I think the most important thing is that it's fun. It's super cool to be able to work in this space and just have a new problem and a new challenge to tackle and have such a wide playing field. Even though I'm interested in immunoengineering, and although that might sound specific, there's so many different things I could work on. I could work on cancer vaccines. I could work on T cell engineering. I could work on immunotherapy blockade. Like, it's such a diverse environment, and who knows what more new fields are going to be created in the coming years and in the coming days. So hopefully in all of that, I know it must have been a dense couple minutes, but I'm hoping I was able to give you some insight into biomedical engineering, how you can pursue a career in the field, and what one person's career path looks like. And again, I want to say the disclaimer that this is one person's career path. There's no right choice. There's no perfect path to get to where you want to go. A lot of it is just about learning along the way. So before jumping into the Q&A, I just want to share some additional resources and some ways to connect if you would like to reach out and ask me questions after this workshop. If you want to learn a bit more about my research, here are some resources you can look into. These are QR codes. So if you want to take your phone and turn to the camera, you can scan the QR codes and it should take you to those resources. I did do a TEDx talk last year. It feels like 2 years ago. Time is so weird right now. But if you would like to learn more about why I think, it's important to get involved in STEM at a young age, which is why I was so glad to see that a lot of you are high school students. I think it's awesome that you're venturing into STEM already. You can never start too early. And also, if you want to learn more about my research and the work that I've done, you can take a look at that article. And if you're interested in applying for research internships and want to learn more about how to approach that, I'm happy to discuss it in the Q&A if you'd like. But there is this great resource from UC Berkeley that walks you through how you should cold email professors and what's the best way to apply for research internships. And also, if you want to learn more about drafting a CV, which is a research-specific resume, CV stands for curriculum vitae, or even if you want to learn about what is the best way to draft a resume for research internships, there's a great resource right here from UC Davis. And finally, if you want to connect with me, you can reach out to me on LinkedIn or follow me on Twitter. And less conventionally, throughout this quarantine period, I actually started a Nailer account where I share a lot of the STEM facts and STEM knowledge that I've gained throughout the year and throughout my experiences in the form of nail art, because I love nail art, love STEM, figured why not combine the two. So if you want to check out some of my nail art, feel free to check me out on Nacreous Nail Art on Instagram. And with that, I wanted to thank you all for your attention and let you know that I didn't choose the engineering life, it chose me. So at this time, I'd be happy to take any questions. Feel free to unmute yourself, or if there are any questions in the chat, I can take a look at that as well. But yeah, thank you so much for inviting me to do this workshop, and thank you all for your attention.
Everyone, let's give Netra a big virtual round of applause.
Thank you.
At this time, feel free to drop any questions in the chat, but we will be starting with some of the questions that were sent in through the RSVP form. Camila, do you want to read those out?
Sure, I'm gonna read you the question from the RSVP. So the first one is, how can I prepare to study biomedical engineering in college as a high schooler?
Yeah, that's a really great question. So I think the main thing is to identify courses that you want to pursue or programs that you want to apply for. So a lot of these websites will have a list of courses that are used to evaluate your admissions average when you apply to the program and what courses are required for you to be considered a valid applicant for the program. So highly recommend you take a look at those courses. For me, the undergraduate program that I was applying to, funnily enough, did not require biology. And I was in the International Baccalaureate program when I was in high school. So I could only take 2 sciences, couldn't take all 3. So I ended up taking chemistry and physics because both of those were required courses, but biology wasn't. So I supplemented my biological understanding through reading and the research internships that I did in high school. So I think the best thing would be to identify programs you want to apply to, look at the courses that they require, and make sure you're able to fit those courses into your high school curriculum.
That's so cool. So the next one is, how do you know you wanted to go into biomedical engineering, and what does being a biomedical engineer entail exactly?
Yeah, so hopefully I was able to address that question through my presentation. But I think what really made me interested in biomedical engineering was the fact that I really enjoyed mathematics and chemistry and physics and biology. And I was looking for a field that would allow me to integrate those concepts and allow me to bring those concepts together to tackle challenging and innovative problems. And I think biomedical engineering really afforded me that opportunity because, as you saw earlier, it is such an interdisciplinary field. So it's a really cool way for me to bring in all of these subjects and concepts that I really enjoy. So I knew right off the bat biomedical engineering would be a good path for me. And what does being a biomedical engineer entail? And again, in my presentation, you saw that being a biomedical engineer can look really different because there's a lot of things that you can do in the field. You can pursue a PhD, you can pursue a master's, you can work in a company, you can work as a scientist, you can be a doctor, and all of these still fall within the realm of biomedical engineering. So that question is a little bit harder to answer, but in my context, and for me, being a biomedical engineer looks like being a PhD student and working in a lab, designing my own project and pushing that forward.
All right. How did you decide your career, and what kind of path did you take in college?
Yes. So again, you were able to kind of see a visual of the career path that I took. And I really think what led me into pursuing a PhD was the fact that I was able to do research internships throughout high school and undergrad. And I think research is something that you just have to try to figure out if it's something that appeals to you and something that interests you. So if you all can try it out at least one point in high school or throughout your undergrad degree, highly recommend you try to do a research internship. And hopefully that'll let you know if that's a good way for you to move forward, or if that's not something that really appeals to you.
What kind of facilities can I work at as a biomedical engineer?
Yeah. So uh, I think right off the bat, there's definitely, the distinction between academia and industry. If you want to work at a university in a lab, you generally follow the academic path. And if you want to work in a company, you would follow the industry path. And again, both of those look different depending on the field that you're in and the role that you have within that environment. So that question is a little bit hard for me to answer, but I highly encourage you to look into those resources that I shared, so you can get a bit more of insight and a wider perspective from people who are in these different areas, because ultimately they can give you the best insight possible.
What would you recommend for a freshman in biomedical engineering to do to ensure a pathway in the career?
Yeah, I think a big thing about your undergraduate degree is being willing to explore. I think it's really beneficial to try out these different areas, um, and and try out different fields of research, because until you try it out, you won't know if you like it or not. So, as a first year, I think the most important thing is to keep an open mind and try to find opportunities you can pursue, and try to find research internships that you can apply for. A lot of it might be self-driven, and you might need to put in a lot of effort on your part to actually Google these internships and reach out to professors. But I think having that open mind and taking that initiative is really worth it, and will ultimately help you carve out the path that you want in your career in biomedical engineering.
They are so great tips. Thank you so much. And the other questions are pretty much the same, so that would be it.
I can read out some of the questions that were private chatted to me. I think
Sure.
you kind of answered them in your last question, but a lot of people are asking, do you have any advice for high school students on how exactly to look for internships and how to apply to them?
Yes, for sure. So I think with COVID, a lot of these are challenged in some way, but I also think it opens new doors because everything is virtual. You have the opportunity to read up and work with people remotely in a virtual setting. So I think the really cool thing that, or the more critical thing that I would encourage everyone to do is to read up on areas that interest you. For me, I knew I kind of had this interest in cancer, so I started reading up a lot on papers in cancer research. I started reading up articles to figure out what were the latest advancements and things like that. So, if you already have an idea of an area that interests you, try to read up more on it and figure out who are the key players in that field. Or if you know of institutions near you, maybe look through the faculty list and see which profs are working on these areas that interest you, and send them an email. Say, I'm a high school student. I'm really interested in this area. I've read up a bit about this, and I'd love to chat with you sometime to get your insight into the field and figure out, if you have any virtual projects that you're looking for students to help volunteer on, things like that. So again, I think that UC Berkeley resource is a useful resource to look at if you actually want to figure out what is the best way to draft a cold email to a professor. And um, I don't want to discourage anyone, but professors are very busy. So it might take a couple of tries before you actually get a response, but don't be discouraged. You have to continue persevering, continue sending out those emails, continue reaching out to people. And I guarantee once you send out a couple of emails, at least one will respond back. Yeah,
Thank you so much for the helpful advice.
no
Another
problem.
question was, what are some successful qualities of a biomedical engineer?
Yeah, that is a very good question. I think the specificity of qualities would very much differ depending on which area of biomedical engineering you're in. But I think an overarching quality that all engineers and I guess just everyone in STEM should have is curiosity and knowing how to ask the right questions. And I don't think this is a quality that people are born with. I think a lot of it is you kind of throwing the net as wide as you can and asking a bunch of questions. And eventually, as you advance in your career, you start figuring out what are the good questions to ask, which ones lead to impactful results and impactful experiments. So I think being curious and knowing how to ask the right questions is a very important skill for a good biomedical engineer. In terms of soft skills, I think also communication is a really important skill to have. You're going to be sharing your work with a lot of people, and not all of them are going to be scientists. So you need to figure out how you can distill the technical concepts of your work and make them more accessible to a wider audience. Ultimately, if you can communicate your work well, you'll be able to get funding to pursue that work. You'll be able to push it forward. So it's kind of a cycle. Yeah, I guess if I were to distill it into three general qualities: knowing how to ask the right questions, being curious, and communicating.
Great, thank you. Another question was how much math and physics is involved in biomedical engineering, and can you still pursue this area of study if you're not the best at math or physics?
Yeah, the answer to that question is it differs based on the area. If you are working at the intersection of mechanical engineering and electrical and computer engineering, I could imagine there being a larger proportion of physics and mathematics involved. But that being said, because you are in the realm of engineering, there is going to be some extent of math and physics involved. Um, and to the point about can I pursue biomedical engineering if I'm not good at it? I think the answer is you don't have to be born good at anything if you are going to be pursuing biomedical engineering or any field for that matter. It's all a learning process, and a lot of schools do a really good job of bringing in those foundational concepts so that you're able to grasp them and learn how to apply them. So the short answer is yes, you can definitely pursue biomedical engineering if you're not good at math and physics, but the hope is that throughout your education you will have a better intuition for these concepts, and then eventually you won't be bad at them anymore, if that makes sense.
Yeah, that was a really good answer. And I think this is the last question for now. If you could talk to your past high school self, what advice would you give them for studying BME in college?
Mm. Um, I think the advice that I would give is to be open minded. I think to some extent, with my interest in cancer research, I already closed off a bunch of other areas because I knew like this is something that I was really passionate about. And I don't think that is the best thing to do because when you're starting off, you're pretty naive in the sense that you've only had exposure to this one thing, and if you love it, that's great. But I also think, if you love it, you should try out something else because you already know that you love it. So, yeah, I would just say be open minded. Don't be afraid to reach out to people. Don't be afraid to take initiative. It was really scary for me to cold email a professor because these people are super busy and they're way up there. But eventually, I had my family and friends around me supporting me, and they were like, "Just go for it. Just send the email. You have nothing to lose." And after I sent out those emails and got a response, I realized, wow, yeah, what Wayne Gretzky said is true. You miss 100% of the shots you don't take. So just go out there, take those shots, take the initiative, um, and like when you talk to people and people like me who say, feel free to reach out if you have questions, take advantage of those connections, reach out, ask those questions because you never know who's going to help you down the path. So I just want to shout out again if anyone wants to reach out to me, feel free. Happy to connect and happy to help out and answer your questions as they come down the path.
Thank you so much for that encouraging answer. And I think one more question rolled in. How do you come up with ideas for your research, or how do you find opportunities?
Yeah, I think the really the best way to do that is to figure out what other people have done. And the only way to figure that out is by reading through literature. So, as I said, If you find an area that interests you, try to read up as much as you can on that area. Look into scientific papers, look into articles. There's a great type of article called a review article, which, although it might contain a lot of technical jargon that you might not understand right off the bat, generally these review articles are an overview of an area so that you can get insight into and have a bigger picture of what that area is about. So if there's an area that interests you, just Google the name of that area plus review article and see what comes up. Read up on those review articles and see what people have done in the field. And as I said, a lot of these scientific papers will say this is what we've done, but this is what should be done to push the field forward. So those are also really good avenues for you to get ideas on what is the next direction to move this field forward. But from a student's perspective, a lot of this thinking and ideas come later on in your life. So for example, right now I'm a PhD student, and a lot of these project ideas would be generated by me in conjunction with my PI, or the principal investigator, the professor that I'm working with. But early on in your career as an undergraduate student, or a high school student even, you'll have people around you who have been through the PhD experience, are familiar with how to think and how to ask the right questions. So generally they'll have a project idea and you'll kind of hop in on that project and help them out with the experiments that they need or work that needs to be done. So earlier on, you don't necessarily have to have your own project idea, but definitely as you move on later, the best way to come up with those ideas is to read as much as you can and stay educated.
Great, wonderful. Does anyone else have any other questions that they want to drop in the chat?
Or if you want to unmute yourself and ask.
Yeah, feel free to unmute yourself.
I would love to hear your voices. No pressure though. I understand Zoom is definitely a very interesting way to have these conversations.
Definitely. All right, I guess no one has any questions. Then I guess we can end it here. Thank you so much for attending the workshop, everyone. And thank you so much, Netra, for speaking at this workshop. And
Yeah, my pleasure. Thank you so much for having me.
No problem. Happy Thanksgiving, everyone. And I hope you guys were able to learn a lot.
Yeah, have a great Thanksgiving and happy holidays. Take care, everyone.
Bye.